Hello, Energy 101. Today we're going to talk about energy quality. We talked about the first law in the law of conservation in the last module, that all the energy in has got to equal the energy out. And in the introduction to energy conversion, we talked about all energy does not have the same quality. That's really the outcome of the second law of thermodynamics. But today we're just going to introduce the concept of quality and dig a little deeper into what that means. We know that from energy conservation, when we're converting energy, that all the energy inputs on the left here have to equal all of the energy inputs. So we sum all those quantities up, they have to equal the sum of all the quantities out. The forms we can convert from one form to the other. We can convert chemical energy into heat energy by combustion, for instance, chemical energy and fossil fuels, but the energy content on the right-hand side has got to equal the energy that you put in. We just talked about that. Now we're going to talk about the fact that all of these energies over here that we put in do not have equal value or quality, and same way, of course, on the right. So what do we mean, and what's the situation with energy quality? Well, the work, electricity, kinetic energy, and radiation are just some examples, all of which have an energy quality of 1. Now we grade quality as on a scale, a little bit arbitrary, of 0 to 10. And work, electricity, kinetic energy, and radiation is, by the way, potential energy. I could add in here, I could add several more types of energy, but these are the ones that we deal with and are most familiar with. All of those forms have a quality of 1, and they can be converted from one to the other theoretically, ideally, on a one-to-one basis. If we have friction and some losses in the real world, then that's not totally true, but almost. The work, we of course convert it, produce it with a power plant, then we use the work to produce electricity to turn a generator. The source energy is, of course, fossil fuel, so we're converting fossil fuel to work. Electricity, with a generator, we produce the electricity from work input. A wind turbine. A wind turbine takes the kinetic energy in the wind and converts it to another form, electricity or shaft work to turn the generator in the turbine module itself. Radiation, of course, the example there is sunshine, and we use a solar cell or a photovoltaic cell, we call it, to convert the radiation coming from the sun into electricity. But the radiation coming in has a quality of 1, kinetic energy has a quality of 1, electricity has a quality of 1, work has a quality of 1, potential energy has a quality of 1 also, which isn't in the list but could easily be. Now, so what's the big deal? Looks like most of the energies have, forms of energy have a quality of 1. Well, the problem is that thermal energy or heat has a lower quality than 1. And it varies with the temperature of the thermal heat. Some things are hotter than others, and the hotter they are, then the more quality the energy they contain have. Generally, the more energy they contain, the hotter it gets, but also the quality of that energy per unit is higher also. And unfortunately, most of our energy comes from burning fossil fuels, and that produce heat. So we're getting most of our energy from thermal energy or heat that has a quality of less than 1. And that's one thing that's hard for us to comprehend or get our heads around, because it's not really intuitive. But that's the bottom line, the most key aspect of talking about energy quality, is that thermal energy, which is sometimes termed heat, and they're synonymous with the way I will use them here, does not have the same quality per unit of energy as work, electricity, kinetic energy, or radiation. That's the takeaway here. Well, what is the quality of thermal energy? Well, it varies with the temperature that the thermal energy or heat exists. And here's the equation that's sometimes called Carnot equation, but not going to get into that. We're not going to make thermodynamicists out of you, but we want you to understand the limitations that nature puts on our conversion processes. The heat quality or quality of thermal energy is calculated as 1 minus the temperature of the atmosphere, whatever the ambient temperature is. It may be the river temperature, the air temperature, whatever is the ambient in our system that we're using, that we place the ambient environment, we place the system to generate energy from the heat. Temperature on the denominator is the temperature of the thermal energy. If it's a hot cup of coffee, it may be 100 degrees Fahrenheit. If it's waste heat coming off of a boiler in the stack, it may be 200 degrees Fahrenheit. But the other thing we'll get to in more detail next module is that the work that we can get out of this heat is capped and limited by the quality of the heat. And notice that the inequality makes it a negative statement, as all statements of the second law does. As an example here, they just looking at a graph, the higher the temperature, this is on the bottom scale, is the temperature that the thermal energy exists. And if we move to the right, then the quality of that energy moves upward. And it approaches 1, it doesn't exceed 1 no matter how high the temperature gets, but it approaches 1 as the temperature goes off to infinity. So if we have an infinitely high temperature, then we do have thermal energy with a quality of 1. But the problem is that situation melts anything that we try to contain it in, and we have to have metals and materials to operate at that combustion temperature to extract that energy and utilize it. So we have a limitation on the temperature that we can use and get from that thermal energy. But the other big aspect, the takeaway here I want to point out is that the temperature that you plug into this formula is Rankine temperature, not absolute, not Fahrenheit, but what we call an absolute temperature Rankine. And I'll just quickly look at an example here. If we have waste heat that's available at 240 degrees, then what is the quality of that thermal energy per unit of energy? And we look at the formula, and it's 40 degrees Fahrenheit, but we have to convert it to a Rankine. Well, the way we convert Fahrenheit to Rankine is you add 460 degrees to it. And so you have to have Rankine temperature in the numerator and Rankine temperature in the denominator. So I'm assuming the ambient temperature is 40 degrees Fahrenheit on a cold day. The rivers are cold, lakes are cold, or whatever the ambient is, and that the waste heat is available at 240 degrees wherever it's coming from. But we have to add 460 in order to convert to the Rankine. So converting Fahrenheit, 40 degrees Fahrenheit to Rankine, we get 500 degrees Rankine. 240 degrees Fahrenheit, we get 700 degrees Rankine. Plug it into the formula, and we come out with a 29% quality for 240 degrees. Now, obviously, if I put in a higher TH here that my thermal energy exists at, then I'm going to get a higher number than 0.29. Notice this temperature of the thermal energy keeps going up with a constant ambient temperature. Then this second term goes to 0, and I approach my quality of 1 that I mentioned, but that's an impossible real-world situation to get an infinite temperature. So that's a sample calculation, and what the second law tells us about that quality is that less than 30% of that 240 degree thermal energy can be converted to work or electricity. That's really a statement of the second law that we'll get more into next time in the next module. But that's the concept of quality and the way that we calculate it And I hope that gives you a little bit of intuition and a feel for the limitations of the second law. Now, one thing, again, that we are comment on that makes the second law difficult to grasp is that almost every other law that I can think of, all of them as a matter of fact, the natural laws, they are equalities. They're positive statements. They tell you what has to equal what. The mass going in has to equal the mass going out. The energy coming in has to equal the energy coming out. F is equal to ma, Newton's law. All the other laws of the physics and nature are expressed as equalities. But the second law is a negative statement. That's with a less than sign, then that means it's a negative statement. Now, unfortunately, that means that you can state the second law of thermodynamics in infinite number of ways. So we'll talk about that a little more, but that's the hardest issue with the second law that makes it a little difficult to comprehend and try to get it intuitive to grasp. And this just shows on a graphic, in a graphic manner, the fact that as the temperature goes up, the quality goes up, and at ambient temperature down here, we, of course, our equation tells us 1 minus T ambient over T ambient, and so you have 1 minus 1, so I have zero quality energy if my temperature is ambient, which means all of this energy in the atmosphere due to the molecules bouncing around, and there's gigantic quantities of energy in the atmosphere, and the oceans, because all those molecules are bouncing around too, and that they have no quality. So we can't do much with them if they have no value. That's why they're free. Nobody's charging us to get energy from the atmosphere because we can't do anything with it and it's free. Okay, so that concludes the concept of quality that comes from the second law of thermodynamics. Thank you. We'll talk about the second law in more depth next time.